All right, in the next lesson, we're going to talk about the magnetic force between two parallel wires, two conductors that have a current going through them. First, let's talk about the direction of the force, whether they attract or repel each other. Going way back, if you remember, we talked about having two little bar magnets side by side next to each other. And we said, and I'll put it right back up here, this is from page 3, that if I've got two bar magnets where the magnetic fields interact and they're in opposite directions, they cause them to attract each other. If I've got these two little bar magnets next to each other, where the magnetic fields are in the same direction, they're going to repel each other. Keep that in mind. Magnetic fields in the same direction cause repulsion. Magnetic fields in opposite direction cause attraction. Let's take a look at these two wires here. Both cases, the current is going towards the bottom of the page. So let's figure out the direction of the magnetic fields going around each of those wires. Positive charge flow. My thumb points in the direction of the current flow, and my fingers wrap around in the direction of the magnetic field, which means on this side of the wire, the magnetic field is coming out of the page, and on the other side of the wire, it's going into the page. So I'm going to draw, for this case, I'm going to draw dots here, showing the magnetic field coming out of the page, and X is here. And since it's an identical wire with the same direction of current flow, I should get the same magnetic field. Notice that in between them, magnetic fields are in opposite directions. They're in opposite directions there. So these guys are going to wind up attracting each other. Conversely, keep the same hand rule. Well, this guy is virtually the same as those two over there. So if I want to do my hand rule, I can. But I know it's coming out of the page on the right-hand side into the page on the left. So, dots here. X is here. This one, turn it around. There's my thumb going this way. Dots here. Out of the page here. X is here. Going into the page. Notice that these guys are in the same direction, which means they're going to repel each other. So when the currents wind up going in the same direction, the magnetic fields interacting in opposite directions, they attract. Currents are in opposite directions, the magnetic fields between them are in the same direction, they're going to repel each other. Fair enough. Now, let's say we want to find out just how strong that force is if we happen to know the distance between the two wires and the current between those two wires. Now, we won't really be able to get the force itself. We'll be able to get the force per unit length on the wire, and we'll see where that goes into. Now, let's think about wire A as if it's sitting in the magnetic field wire B as if it's sitting in the magnetic field caused by wire A. So, wire A, magnetic field's coming out of the page on this side into the page there. So I've got a magnetic field coming out of the page here, and wire B is sitting in that magnetic field, which is being generated by wire A. Well, one thing we know is that the magnetic field caused by A is going to be equal to the constant times the current of A divided by 2 pi r. R is the distance between wire A and whatever point you want to find the magnetic field at. At this point, it's where wire B is sitting, and that point in wire A's field. So, that would be the magnetic field strength of A where B exists. Magnetic field of A. Now, we also happen to know that it's pretty simple to find what the force on wire B is if we happen to know how strong the magnetic field, that external magnetic field that B is resting in, if we happen to know the length of B and the current going through B. So the force acting on wire, and this would be the force acting on wire B. Now it's going to be the same either way because of action-reaction. Whatever B gets, A is going to get also, equals the current from B times the length of that wire times the strength of the magnetic field that it's sitting in, which of course is being generated by wire A. Now, we know that the field being generated by wire A is U0 IA over 2 pi r. So I'm going to put that right in there, mu0 IA over 2 pi r. And then we're just going to rearrange this thing a little bit. We're going to put the L on the other side. So we're going to get the force per unit length on either one of these wires. That's how many newtons per meter. It's not really a spring constant, all right? Just saying that if I've got a force per unit length of 2 newtons and I've got a wire that's 3 meters long, that means it's going to be 2 newtons per meter times 3 meters long means you'll have 6 newtons acting on the wire. And that's going to equal mu0 IA IB over 2 pi r. Fair enough.